Hi everyone. In this video, we are going to discuss on tutorial 13. The topics is Young two-slit experiment. So we go to question 1. The figure shows the interference pattern formed on the screen in a Young two-slit experiment. The separation between the slits S1 and S2 is 0.18 mm and the screen is 70.0 cm from the two slits. The distance Y is 6.4 mm. So question A, what is the phase difference between light waves from S1 and S2 at the points 1 P and then 2 is point O. Okay, so given here at point P, the the pattern formed here is a dark fringe. So that's mean it is destructive interference occurred here. Okay, so the formula path difference is m plus half bracket lambda for the dark fringe. Okay, so we are going to find what is m at point P. So we start from the middle here. The center bright maximum will be at O. So this is the first dark fringe from the formula. M0 is 0 plus half times lambda, so we get half lambda. So that's mean here is m equals to 1. So the path interference will be 1 plus half lambda. And at point P, m will be 2. So 2 plus half lambda. So we get the path difference equals to 2.5 lambda. Now we convert this to the radian because the question asks for phase difference. So the phase difference in radian. This is path difference. So you must know the difference between path difference and phase difference. So phase difference, the unit is radian. So convert this to radian, we get 5 pi radian. You can use a ratio method to convert to radian. So we know that half lambda is equals to pi radian. So when 2.5 lambda, so this is what you're going to find. You can use a ratio method and you get 5 pi radian. So that's the answer. So then the question at O, phase difference at O. So O is in the middle. This is a central bright maximum. So that's mean from bright fringe, the constructive interference is m lambda. Okay, the formula path difference is m lambda. So m at the center O here will be 0. So phase difference also is 0 because path difference 0. So phase difference is also 0 radian. Okay, now we go to question B. Calculate the wavelength of the monochromatic light. So we can use formula y equals to m lambda d over A. So A is the separation between the slits. D is the distance from the screen to the slit where m is 0, 1, 2, 3 and so on. Okay, so y is given from O to P. So we count how many y there. Y is distance between bright to next bright. Okay, so we start from here lah. The P is dark, so next is bright. You can see y there, start from the bright. So bright to the next bright will be 1, and then next bright, second next bright, third next bright, and the fourth bright. So altogether 4 bright. So that's mean y will be 1 over 4y. Okay, so this y is distance between the two neighboring bright fringe. So now we get 1 over 4y. So we substitute 2 m equals to 2 because just now m is 2. Okay, calculated already in A1. So m is 2. Middle here 0, 0, 1, 2. So m is 2. Then the distance 70 centimeter. Okay, and the slit separation is 0.1 millimeter. Convert to meter. So we calculate, we get wavelength equals to 4.11 times 10 to the power of negative 7 meter. Okay, so that's the answer for the wavelength of the monochromatic light used in this interference pattern. Okay, question C. What is the optical path difference between light waves from S1 and S2 at point Q? Okay, so now we look at point Q. So the questions one, optical path difference. So optical path difference, S1 to Q, and then another one is S2 Q. So the path difference will be S1Q minus S2Q, because S1Q can be seen here in the diagram is longer than S2Q. So optical path difference will be S1Q minus S2Q. Okay, this is equals to the uh, path difference. Path difference will be delta L. So we use this symbol for delta L. So we can use trigonometric ratio to find delta L from the right angle triangle here. So we use sine theta. Okay, sine theta opposite over hypotenuse. So the hypotenuse will be A, the separation between S1 and S2. Okay, so we write as delta L, and then using trigonometric ratio, so sine theta equals to delta L over A. Okay, now to find delta L, cross multiply, we get A sine theta. But the problems here, we don't know theta, okay, but we can use formula A sine theta equals to M lambda for M order. So we use order just now calculated is 2. Okay, so we substitute order 2. Lambda also calculated in B. And A given 0.18 millimeter, convert to meter. And we get angle theta equals to 0.262 degrees. And we substitute into here. And we get delta L, which is path difference, is 8.23 times 10 to the power of negative 7 meter. Okay, actually we can also use another method where delta L is equals also M lambda. So M we know already, it's 2, and lambda also calculated in B. So this is the shorter method. So M2 times the lambda in B calculated here, and we get the same answer. Okay, same answer. Okay, so now we go to question 2. In a young two-slit experiment, monochromatic light of wavelength 500 nanometer illuminates the two slits which are separated by 0.12 millimeter. So calculate the angular separation in radians between the interference fringe. Okay, so the formula A sin theta equals to M lambda. Then separation is 0.12 millimeter, convert to meter. Sin theta equals to 1 times the wavelength, 500 nanometer, convert to meter. So we calculate, we get angular separation. Theta is 0.239 degrees. Okay, so now because the question asked to write in radians, in radians, so we convert to radians. You can use the ratio method. We know that 180 degrees equals to pi radian, or if 90 degrees is or half lambda, okay, is a pi radian. So in this case, 100 we can use 180 degrees also. Okay, this is half lambda, 180 degrees is half lambda. Okay, for 0.239 degrees, so how many radian? So we use ratio, we get this, and the answer is 4.17 times 10 to the power of negative 3 radian. Okay, so that's the answer, angular separation in radians. Okay, now we go to question 3. Draw the interference pattern produced in a young two-slit experiment when the light used is green and then red. So clearly explain the difference between the interference patterns. Okay, so this is the patterns. The green for the green and for the red. So the middle here is the center bright maximum. Okay, you can see here, we know that wavelength for red light is larger than wavelength for green green light. Okay, so from the formula, y equals to m lambda d over a. So here, lambda increases, so that's mean the y also increases. So y is the separation between the fringe. So you can see here, the width of the red fringe is greater. Okay, so width of the red fringe is greater compared to the width of y green. So okay, so this is the answer. Okay, now we go to the question 4. Okay, red light of wavelength 680 nanometer is used in a Young's two-slit experiment. The separation between the two slits is 0.15 millimeter, and the interference pattern is observed at a distance of 85.0 centimeter from the two slits. So draw a sketch of interference pattern produced. Okay, this is for red light. So the interference pattern similar to question 3 just now, but just for red. Okay, so this is the pattern. Now we are going to calculate the fringe separation. So it's y. Fringe separation is equals to y. So the formula is m lambda d over a. So m for separation, we can start from the m0. So m0 to m1. So that's why m1, we use m1. Lambda is 680 nanometer, convert to meter. Distance is 85 centimeter from the slit to the screen. Okay, then separations of the slit is 0.15 millimeter. So convert to meter. So we get the answer. Fringe separation is 3.85 times 10 to the power of negative 3 meter. Okay, and lastly, the question C. One of the two slits is covered by a thin translucent film of refractive index 1.4. So the central maximum is displaced to the position of the 8 dark fringe of the original interference pattern. Calculate the thickness of the film. Okay, so now we put a thin film on the covered the slits. Okay, the two slits. Okay, so refractive index is given, so that's mean we can use optical path. So optical path formula is n times d. Okay, n is the refractive index, d is the distance the light travel. So optical path difference will be nt for film minus na for film. So this is the path difference, okay, which is equals to a path difference delta L, and delta L is m lambda. So the m is equals to 7.5 lambda, because mentioned here of the 8 dark fringe. Okay, dark fringe. Okay, so how to imagine this? Okay, I help you by the diagram. So this is the original bright fringe. Okay, central bright fringe. So it is at the 8 dark fringe. So this is dark fringe is in the middle here, between label with 1 here. So this is first dark, second dark, third dark fringe, fourth, and so on. 8 dark fringe. Okay, mentioned here 8 dark fringe. So by order M, okay, by order M, we start from the center bright. So this is M0, this is M1, M2, and so on until M8. M8. So that's mean the new position is here. Okay, so counted for dark fringe, so we get 7.5 lambda. Okay, so now we can solve. So for the film, the slits, the two slit we covered with the film. So let's say the thickness of the slit is T. So originally it's air, air. So Na times the T, and the distance T is replaced by the film. So that's why the path difference will be n film T minus n air T. Okay, so now we substitute the n of the film, refractive index of the film 1.4t minus n air is 1. So 1 times t is t equals to 7.5 lambda, and we solve for t. So we substitute lambda given 680 nanometer, convert to meter, and the refractive index 0.4, and the refractive index say 1.4 minus 1, so we get 0.4. So the answer, the thickness of the film is 1.28 times 10 to the power of negative 5 meter. Okay, so that's the answer for question 4. Okay, now we finish tutorial 13 and see you in the next tutorial. Bye bye.